In this video, we're going to start our discussion on rational functions. We'll learn what a rational function is and how they differ from polynomial functions that we've been working with. We'll also be looking at some examples of rational functions and their graphs. First off, a rational function is a function of the form f of x equals p of x divided by q of x, where p and q are polynomial functions. So essentially, a rational function is just a fraction of polynomials. Let's take a quick look at some examples of rational functions. Something like f of x equals 4x minus 1 divided by x squared plus 3x minus 10 is a rational function because it's a fraction of two polynomials. In the numerator, we have the polynomial 4x minus 1. In the denominator, we have the polynomial x squared plus 3x minus 10. Another example could be something like g of x equals 2x squared plus 3x plus 1 divided by x squared minus 2x minus 3. Because again, we have a fraction of two polynomials. 2x squared plus 3x plus 1 in the numerator, x squared minus 2x minus 3 in the denominator. Let's look at one more. Something like h of x equals x divided by x squared plus 4 is an example of a rational function because we have a fraction of two polynomials. One thing that's different about rational functions is their domain. When we were working with polynomial functions, the domain was always all real numbers, since we didn't need to worry about square roots of negative numbers or dividing by zero. However, when we work with rational functions, we do have to worry about dividing by zero. So the domain of a rational function is usually not all real numbers. Instead, their domains are all real numbers except for the x values that make the denominator equal to zero. Let's go back to our three examples of rational functions and try to find their domains. So first, let's try to find the domain of the function f of x equals 4x minus 1 divided by x squared plus 3x minus 10. The domain of this function is all real numbers except for the x values that make the denominator equal to 0. So how do we find those x values? Well, all we have to do is set the denominator equal to 0 and solve for x. So we have x squared plus 3x minus 10, set that equal to 0, and solve this equation. We can try to solve this equation by factoring. To factor x squared plus 3x minus 10, we need to come up with two numbers that multiply to negative 10 and add up to positive 3. Two numbers that multiply to negative 10 and add up to positive 3 are positive 5 and negative 2. So this factors into x plus 5 times x minus 2. And this is equal to 0. Whenever the product of two things is equal to 0, that tells me that either the first factor equals 0 or the second factor equals 0. So we can split this equation up into two parts. We either have x plus 5 equals 0 or x minus 2 equals 0. And we can solve these individual equations. On the left here, subtract 5 from both sides to get x equals negative 5. And on the right, add 2 to both sides, we get x equals positive 2. So these are the two x values that make the denominator equal to 0. So our domain is going to be all real numbers, which I'll write as the interval from negative infinity to infinity, except for the x values, negative 5 and 2. So that's how we find the domain of a rational function. Now, before we move on to our next rational function, let's take a look at what the graph of this function looks like. Let's type our function into Desmos to see its graph. We have 4x minus 1 divided by x squared plus 3x minus 10. So this is the shape of the graph of our function. Now, if we trace along this graph, you'll notice that we have some things occurring that we normally don't see when we work with polynomials. When we worked with polynomials and we traced our graph to the right and to the left, we knew one of two things could happen. The graph could go up to positive infinity, or the graph could go down to negative infinity. However, this is not a behavior we're seeing for this rational function. When I trace this graph to the right, it seems like my graph is getting closer and closer to the x-axis, and the same thing when we trace to the left. The graph gets closer and closer to the x-axis. So as we trace our graph to the right and left, our graph gets closer and closer to the horizontal line y equals 0. This line that our function gets closer and closer to as we trace along its graph is called an asymptote, and it's something that rational functions have. Now, the horizontal line y equals 0 is not the only line that our function gets close to as we trace along the graph. If we trace our graph getting closer and closer to -5, it seems like my graph will get closer and closer to some vertical line here. Same thing as we get closer and closer to x equals 2. My graph goes down towards some vertical line, and on this side the graph goes up towards some vertical line. Let's type the equations of those lines in to make things more clear. We have the vertical line x equals -5, and also the vertical line x equals 2. Again, we see that as we trace our graph towards -5, our graph gets closer and closer to that vertical line. Same thing at x equals 2. As we trace our graph towards x equals 2, our graph gets closer and closer to that vertical line. One thing that you might observe is that these vertical lines, x equals -5 and x equals 2, are exactly the x values that make the denominator equal to 0. We'll get more into how we find these asymptotes in our future videos. So again, rational functions have these things called asymptotes, which are lines that the function gets closer and closer to as we trace along its graph. Let's now look at some more examples. In example B, we want to find the domain of the rational function g of x equals 2x squared plus 3x plus 1, all divided by x squared minus 2x minus 3. Remember that the domain of a rational function is all real numbers, except for the x values that make the denominator equal to 0. So to find those x values, we set the denominator equal to 0 and solve the resulting equation. So we want to solve x squared minus 2x minus 3 equal to 0. Again, to solve this, we can try to factor that left-hand side. We would need two numbers that multiply to -3 and add up to -2. Those two numbers are +1 and -3. So our polynomial here factors as x plus 1 times x minus 3. Set this equal to 0, and let's solve this. Since we have a product of two things and it equals 0, that tells me that either the first factor equals 0 or the second factor equals 0. So splitting this equation up, we have x plus 1 equals 0 or x minus 3 equals 0. On the left, just subtract 1 from both sides, we get x equals -1. On the right, add 3 to both sides, we get x equals +3. So -1 and +3 are the two x values that make the denominator equal to 0. So our domain is going to be all real numbers, which I'll write as -infinity to infinity, except for the x values, x equals -1 and +3. Again, let's take a look at the graph of this function. So let's type our function into Desmos. We have the function 2x squared, and then plus 3x plus 1, all divided by x squared minus 2x minus 3. So this is the graph of our function. Again, when we trace our graph to the left and we trace our graph to the right, we see that our graph isn't going up towards positive infinity or down towards negative infinity. Instead, it seems like our graph goes towards some horizontal line. This time, our graph isn't going towards the x-axis, instead it's going towards the horizontal line y equals 2. We see that when we trace our graph to the left, our graph gets closer and closer to that red line, and when we trace our graph to the right, it gets closer and closer to that red line. We also see that when we trace our graph and then we let our x values get closer and closer to 3, our graph goes down towards a vertical line. Same thing if I'm on the other side. If I go towards x equals 3, my graph goes up towards a vertical line. Our graph is going towards the vertical line x equals 3. Again, we see that as we trace our graph, it gets closer and closer to that vertical line. On this side, as we trace our graph, it gets closer and closer to that vertical line. In our previous example, we saw that we had these vertical asymptotes at the x values where the denominator is equal to 0. But in this example, we only have a vertical asymptote at x equals 3. We don't have one at x equals -1. When we trace our graph and we get closer and closer to x equals -1, we see that we have this point that's undefined here. The point here is undefined because x equals -1 is not part of the domain of this function. So whenever we have an x value that's not part of our domain, and we don't have a vertical asymptote at that x value, what we have instead is called a hole. It's a point that's missing from our curve. And this is something that you might encounter when you work with rational functions. Let's look at one last example. In example C, we're working with the rational function h of x equals x divided by x squared plus 4. If we want to find the domain of this function, what we need to do is set the denominator equal to 0 and solve for x. So we have x squared plus 4 equals 0. If I try to isolate the x, I might start by subtracting 4 from both sides. This gives me x squared equals -4. And then to get x by itself, we need to undo the square. So we would square root both sides, but this is where we run into some issues. We can't take the square root of -4. And this means that our equation here has no solutions. And that means that there are no x values that make the denominator x squared plus 4 equal to 0. Since there are no numbers that make the denominator equal to 0, we never have to worry about division by 0. So our domain is all real numbers, which we'll write as -infinity to infinity. Let's now take a look at the graph of this function. Let's type our function into Desmos. We have x divided by x squared plus 4. We see that in this graph, when we trace our graph to the right or trace our graph to the left, our graph gets closer and closer to the x-axis. So this time, we have a horizontal asymptote at y equals 0, the x-axis. And when we trace along our graph, we see that our graph doesn't go towards any vertical line. So this graph does not have any vertical asymptotes. So in this video, we learned about what rational functions are. We learned how to find the domain of rational functions, and we saw that rational functions have these things called asymptotes. In our next few videos, we'll learn how to find the asymptotes of rational functions.